Okay, welcome back. Hopefully everyone has finished Project 2. How is Project 2 coming? Or done? It's done, right? Good. Anyone started on Project 3? No one's looked at it? Do get started on Project 3. It takes a lot of time to get everything done. You're not going to really accomplish it in one night, but hopefully it's straightforward what you need to do.
Copy paste.
Copy paste. Yeah, and then fix. And then fix.
What was the paper due last night?
Is that the ethics paper?
Yeah.
Yeah. Did y'all do the ethics paper?
Yeah.
Okay, good.
Yeah.
I was like, why was it due last night? I thought it'd be due tonight.
Yeah, that caught me off guard too, but I turned it in.
Okay, great. Good. You turned it in. Perfect. So today we're going to talk about heaps, which is another type of binary tree. What we talked about last time was a binary search tree, which was a way to basically store data such that a search would always be log in. Heaps are going to be a little different. Their main attribute is that instead of storing your binary tree as a bunch of pointers like with a linked list, you're going to just store your binary tree as an array. And then you'll be able to do some manipulation from there. All right.
I haven't printed anything yet.
Who started the printer? All right. Okay. Well, in these slides, also the nice thing about heaps, just to give you an example, is you can also use it to perform heap sort, and then later on we're also going to use it to perform other operations. Is someone actually printing? All right. Well, I'm fixing this the easy way. There. Now I can now print. All right. So heap sort. It is a very traditional program. Sorting algorithm. Whew. It's also always in login. Is that what we want?
Yeah.
Yes. Okay. Good. So we want a sorting algorithms in login, just like quicksort. Quicksort's usually in login, but worst case it's in squared. While quicksort is generally faster, heap sort guarantees in login, which means for critical time or time critical applications, this algorithm is going to be a lot better. For any type of real-time systems, you want to gravitate towards an algorithm that you can always predict its time or runtime of. All right, so we have two different definitions of heap. Beforehand, we've been talking about the memory, which is really the large, what we say here on the slide, the large area of memory which program can allocate blocks as needed or deallocate them. So this is the memory, and when are we using the heap? Number one.
We create something new.
New, right. When we're doing new, getting a pointer, we're creating something on the heap, the memory. There's also the data structure called the heap. So, sorry guys, it's just how it went in life. They decided to name two different things the same word. But heap, the data structure, is called a balanced left justified binary tree in which no node has a greater value than the value of its parent. All right, well that's a lot of terminology we probably have not gone through yet. Keep in mind that, yeah, these two definitions have a little in common. You need to think of them as two completely separate things. And heap sorts can use the second one. Of course, when we're talking about the data structure, we're using the second definition. All right, a binary tree. All right. La, la, la. Okay. So it's balanced. A tree's balanced. I think I went through this briefly. If all the nodes 0 through n-2 have 2 children, that's one way to think of it. So the one on the left is balanced. The one on the right is balanced as well. Notice the way I think of it is each level except the last is completely full, is when I look at it. But technically you could say if all the nodes have 2 children, that's basically saying the same thing. It's not balanced because we need to have a node right over here. So if you move this guy over here, then that tree would be balanced. Notice that this is just, we're talking about binary trees, not binary search trees. So we're not caring if there's an ordering to this tree. We're just saying, is the binary tree balanced or not? All right, left justified. This is going to hopefully be intuitive. This is left justified. This is not left justified. Namely, if you look at it, look at the bottom, notice all the nodes are on the left. But over here, you're missing a couple over here. So this one's not left justified. because some of the nodes need to be, you could think of shifting it over. So either all the leaves are on the same depth, or all the leaves at depth n+1 are to the left of all the nodes at depth n, aka all the nodes are to the left, hence left justified. You could say right justified would be the other way, but that ends up not being useful at all. Okay. Does left justified make some sense? Victor- Hmm?
No.
Yes.
Some nodes on like the right side, so branches, I guess.
I understand what left justified means, like.
Pictorially.
But I don't see it.
Okay. Oh, are we really out of markers? Oh, that would be lame.
There's one over here. It's a green one.
Oh, yeah.
Do they stock the room with markers, or are you required to bring your own?
There's a cabinet I'm allowed to go to and get markers that students are not allowed to get. So I showed you the paper because y'all can get that, but you can't get markers. All right.
So you say.
You aren't allowed to get the markers. There we go. And I mean, for this to be a binary tree, this could be anything. This is not a binary search tree, just a binary tree. So we're just going to put whatever numbers we want in here. All right. So this is still left justified because it's completely full. So we're going to say, just by definition, this is left justified. If we're going to add one node, in order to maintain its left justifiable attribute, ooh, right in the glare, we have to put it over here on the left. And then the next node would have to be here. And so it's still on the left. Notice that it's going to fill the row up from left to right, is kind of what's going on. You can't put a node over here, because then you're missing a spot here, here, here as well.
I see.
Okay, so everything left has to be filled first.
Yeah.
Gets to the end.
Right, it basically fills it from the left over is the best way to think about this.
I thought you meant like you had to put it all on like, the left side.
Oh, no. Then it'd just be a linked list, and that'd be
Yeah,
ridiculous.
That might be just a linked list.
No. No, just, so not left justified, but if we move that 97 over here, then it would be left justified.
And so it's not sorted, correct?
This one is not sorted. This is not a binary search tree.
Right.
Left justified has nothing to do with sorting. Now you can have a left justified binary search tree if you wanted to, but this example is not a binary search tree. This is just a binary tree. All right. Good. We're good with that now? Excellent. Plan of attack. We need to turn a binary tree into a heap. Well, that's good. Next, we'll learn how to turn a binary tree back into a heap after it's been changed a certain way. And this is the cool part. We'll do this in order to sort an array. Actually, once you create a heap, once you create the structure to heapify something, it's actually very easy to sort it, and you'll see why afterwards. All right, the heap property. So beforehand with the binary search tree, we had the property where everything to the left was less than, everything to the right is greater than. With the heap property, each node is going to have a different attribute to it. If the value in its node is larger or as large as the values in its children. So it's a little different, because we're not saying everything to the left is less than, everything to the right is greater than. We're saying all of its children is less than it. So everything has to be smaller. So for example here, good, it has slide examples. 12 is greater than 8 and 3, so 12 has the heap property. Again, 12, remember we're saying is large or larger, just as large or larger, greater than or equal to. As children, so again this 12 still has the heap property. This does not have the heap property because 14 is greater than 12. How could you fix this so it would have the heap property? Swap the 12 and the 14. Everyone see that? All right, great. Naturally, all leaf nodes automatically have the heap property because they have no children. So binary tree is a heap if all the nodes have the heap property. All right, so every node has to be greater than its children. So that,
And this is completely separate.
then a binary search tree.
No, I was saying from the heap that we've been learning about.
Yes, the heap data structure is something completely different than the heap memory. Again, sorry, that's just they just decided to call both things the same thing. Exactly. I'll try and keep that. Yeah, today we're talking about the heap, the data structure. Good morning, Jonah. So when I talk about the heap today, I'll try and just by default think of the data structure. Okay, so sift up. So given a node that does not have the heap property, you can give it the heap property by exchanging its value with the value of a larger child. And this actually tends to be a very nice feature. For example, here you simply have to exchange the 12 and the 14, and then why do you automatically know that the, actually no, we'll go back to that in a minute. Ignore what I just said. Here you just sift up the 14 and the 12. And we're good to go. And this is, we like to call it sifting up. Notice that the child may have lost the heap property when you do this. So we're going to give us a good example, or are we not going to have an example? We need to have pictures. Hold on, stop this. Give me the picture. Okay, here we go. All right, let's look at this from a construction point of view. I think the example is going to help a lot. And then we can go back and read what we're doing. So you add one value to the heap. Since it's a leaf, you don't need to heapify or sift anything because a node by itself is a heap. You add a 10. Excuse me. What needs to happen? Swap the 10 and the 8. All right, great. Okay, are we done? Yeah, for now. Let's add a 5. Are we good?
Yeah.
All right. Let's add a 12. What needs to happen?
Swap
12 and 10.
You have to sift it
Well,
to the
yeah,
eight
the-
first.
yeah.
We're going to do it with the 8 first. So we swap it with the 8. And now you have the 12. Do we need to swap again?
Yes.
All right. And now we have the 12 on top. Do we need to check that 12 is greater than 5? No. Why don't we need to check that? This is probably the most important thing to understand about the heap. I mean, obviously, looking at it, 12 is greater than 5. But why, when we put the 12 here, we just sift it along the left side? Why don't we have to go and look at the right?
Here I know it's greater than.
Because
10 was already greater.
yeah, 10 was already greater than 5, so 12 obviously has to be greater than 5. That's a very important feature of the heap. You don't need to go and try and search the other paths. You only need to search up once. Ow. Whoop. Other children are not affected. So here you go. Swapping the 10 and the 14 is what we need to do. Do we need to check that 14 is greater than 8? I'm just trying to drive this home because this is the most important thing. No, because 10 was already greater than, and since 14 is greater than 10, we know by the transitive property, there we go.
So from the bottom up, you're just checking to see if the node is bigger than its parent.
Right. And then if so, you swap. And then once it's no longer larger, you stop.
So that's the way you would go about it, bottom up, right?
Mm-hmm. Hence you're sifting up. Yeah, so again, the node containing 8 is not affected because its parent gets larger, not smaller, so we don't need to worry about that. We can exchange the 14 and the 12, and again, we don't have to compare against the 5 because we know that 14 must be greater than 5 because 12 was greater than 5 and 14 is greater than 12. Okay. So here's an example heap after it's been heapified. Notice that this is not a binary search tree at all. This is a heap because every node is greater than its direct children. So it's a little different. Now, let me go ahead and go back on the slides a little about how we did the sifting up, just to make sure that I cover all of our bases. All right, so if it has one node, it's a heap. We construct it by adding a node one at a time in a left justified ordering. If it's the deepest level is full, start a new level, otherwise it goes to the right. For example, we'd start here, we add a new node right there, and if it's full, we just add a new one here. All right, so first off, that's where we add the node. Each time we add the node, we may destroy the heap property, so to fix this, we have to sift up. Each time we sift up, the value of the topmost node shift may increase, and this may destroy the heap property of its parent node. AKA, you have to start with the node you added and move it up the heap until you're done. Yeah, we either reach a point where we're no longer greater than our parent, or we're the root, in which case we're done. All right. And then we went through a quick example of this. Here's a sample heap. All right. Let me pause.